Good afternoon, everyone. I'm here. My name is Ato Sam, currently with Suncor Energy, and I'm here to actually present to you an integrated approach to mine-to-mill optimization. And I chose this topic because we've all been doing mine-to-mill, but we kind of we did a project. I think when I was with Anglo Good, and I felt probably we could share it, with fellow, professionals. And just to note, we are in a Black History Month of February, so probably this is the month, or if you've not been reading about, how other Black stuff impacted the world, I think we could all, start reading to see, our impact into this world, right? Thanks. Okay, so the outline for this presentation is we're gonna go through a mine-to-mill concept. What it entails, what is the integrated approach that I'm talking about, what are some of the case studies, and based on those case studies, what is the upstream and the downstream benefits that was achieved, and then finally the conclusion and the recommendation, then probably the questions and answers. So what is the mine-to-mill concept? As you all know, if you take a typical mining company, it's more based on three main stages, and every mine, and especially for metal mining, it's all about getting the output, that is the gold, right? And the gold or the copper or the iron is cutting through, it's taken from the ground. So definitely we have to break it up through blasting. Then definitely blasting doesn't really get it into the right size to be able to extract the gold. So therefore we go into crushing. So under the crushing, there might be primary, secondary, tertiary, based on the type of rock that you are dealing with. Then the final stage is the grinding or the milling, whereby the gold or the copper or the iron or whatever metal is finally extracted from the rock. So the concept, actually, this mine-to-mill concept, it's more like looking at the whole value chain, right? So as you've gone through the three stages, which is blasting, crushing, and grinding, what we are trying to achieve is, okay, how can we, achieve much, breakage from the beginning, right? From blasting stage, so that what at the end of the day, it will tend to relieve the mill and as much as, new breakage as possible. And the slide down here, if you look at the chart in here, the energy consumption. So if you look here, you can see that, blasting, look at the cost, more like the energy that is being used in this sense is, for blasting, it's not that much when it comes to crushing. So if you take these three into, consideration, these are the factors, they have multiples of 10 when it comes to, energy, consumption. And when you look at even the cost section too, you could see that definitely, and if you've heard, it's actually cheaper to blast or to break a rock with blasting than to actually mill or grind. And again, if you look at this chart in relation to the dollar per ton, you could see that blasting actually, as you increase your powder factor, definitely your blasting cost go up. But what is happening is your process cost, which in this case is both crushing and grinding, actually reduces, and therefore you can see your total cost goes down, right? But there is a point, as we will go through, there's a point that even if you keep on introducing more explosive and stuff, this might go up, but this might be stable. Like you just keep on increasing your cost and stuff, you not see any real benefit. So that is where definitely every mine wants to achieve. What is that point, which we'll go through. see some of the approaches to be able to achieve that. And again, the mine-to-mill concept kind of, it doesn't look like, drill and blast crew or mining is doing their own thing, whilst processing is doing your own thing. So a mining engineer will be concerned about, am I actually, it's like I'm providing a service, right? Am I providing the right service to the crushing crew and to the milling crew? So that is what mine to mill concept is all about. And again, it's all about also getting the team together to also be giving feedback, so that you just don't break the rock and put it on the wrong part. And you said, you tell yourself, I'm done with my work. So looking at the typical gold mining cost, you could see drill and blast is almost like 14%, power 15%. This for an open pit. Processing could take like 28%, crushing 3%, and ancillaries, grid control 6%, load and haul 34%. So this piece here, and as you go through the process, you realize that even if you are to increase this piece maybe by 1%, you saw the fact that you get a reduction in all these processes, right? So that is one other thing. I just wanted to show this slide, because just to see the relation of your drill and blast cost in relation to the other costs. I think the underground too is quite similar, with only probably the load and haul being a bit more in processing down. Then this is also the curve. So as you said, we'll go through it. So what you see here is what normally happens is, as you achieve your fragmentation, as it goes, you break the rock more finer and finer. What happens is, definitely in this case, your drill and blast cost goes up, right? Then you see that your crushing and your grinding also, because they are doing less work now, right? Then your load and haul to becomes easier, your productivity increases, right? But at the end of the day, this is the point that we are looking at the optimum, a point. We don't want, there is a point whereby, irrespective, you even make your, you don't want to blast for it all to become fines, right? Because at the end of the day, your cost, still becomes high, and you don't actually get to, achieve it. So what is the integrated approach? How do we, get an approach whereby every stakeholder within the mine is involved to be able to achieve this? Because at the end of the day, our sole purpose in a mine is to produce whichever metal that you produce it, right? So again, we have to work in an integrated way, not in silos. We have to be concerned, and we have to understand that each person is serving a service or providing a service to the other, right? So this is the integrated design mine-to-mill design model approach that I've I've actually developed, and we put it to test, and still working on it. So we start with, okay, every mine definitely have a resource model. So the resource model actually has all your your deposit, everything about what actually you're going to mine, right? Then definitely this can be reduced to the what do you call it, even the reserve model, to rather define where you're actually going to mine. Then so the mine to mill process, or this design model approach, seeks to actually use this model as a source, and the next stage is to actually conduct a rock mass classification. So once you have your your resource model, you with the help of the geotechnical team on site, you'll be able to actually be able to come up with your rock mass classification. You could use the RMRM or the modified RMI with your RKD or whatever means to actually defining your rock mass properties or physical properties you have on site. Then once you have this, classification, the next thing is looking at doing domain delineation. So definitely, let's say if you have a whole one pit that you're working with, definitely you don't want a case whereby if you take a resource model and the block size is 25 by 25, you don't want to come up with rock mass, or identify each block within, because currently at the end of the day, it's human beings that are going to implement it. We've not reached the level whereby everything becomes automated, and all that you need is that. With that one, if you're able to go into details and actually classify each block, as even as a domain, then we might have the benefit. But currently, we want to make it as simple as possible, because of manpower, also because of the technology have not reached there, right? So with the domain delineation, normally I always advise you shouldn't go even more than 6. You don't want to make it more complex, right? You don't want to make it in a way that every area that you are blasting, the guys at some point the guys become confused actually on the field. So you want to also make it more feasible, practically on the field. So what in this stage, what we do is, once you have your rock mass classification, definitely, and with experience, you could tell that certain areas have similar. So if you come up with maybe 4, 5, 6, depending on the size of your pit and the number of pushbacks that you have, right? Then you come up with this domain delineation. Then once you have this domain delineation, you come up with your the BI, the blastability index modeling. And when it comes to the blastability index modeling, there are various, and the one that I currently recommend is the LILI, which I think is 1996. LILI is a former principal of Western Australia School of Mines, and he came up with a good BI. Before him there were others, and after him we have the Ashby Perka BI scheme. We have the JK MRC by Scott, and I've read some papers whereby LILI is more it's more easier. But again, all these options are there. That it all depends on your rock mass properties and what you want to go for. But this case studies, normally I went for what we call it, the LILI. So the LILI actually goes looks at your rock mass prescription, takes into consideration your joint plane spacing, your joint plane orientation, your specific gravity influence, and your hardness, right? And one good thing about LILI indexes, it actually closely correlates with your powder factors, right? And then all of us know that powder factor is a key factor in determining rock fragmentation, and again provides an idea of how your drill and blast design must look like for each plasticity index. If you want to use the HB, actually focuses more on your fracture frequency and effective friction angle. So all these, if you're a mining engineer, you want to come up with such an integrated design model, you have to actually consult your your geotechnical expert on site to actually understand which model or which BI scheme will be effective for you. When you talk about the JKMRC, its approach is to classify the rock mass according to the properties known to affect blasting performance, and taking into account the objectives of the blast. So all of it can work, but again, this when you talk to your geotech guy outside. So once you have this, so what is going to happen is that you now have developed BI for each of these domains. Then once you have the BI, you can actually go on to design your your drill and blast parameters based on this BI. So there is a model that you could actually come up with your BI drill and blast parameters based on this. And again, this is where we'll go through and see you can use your Kushram. So the Kushram, if you look at the Kushram model, the Kushram model actually deals with it has so many parameters, the diameter of the borehole, the powder factor. So whichever your objective is, every mine has an objective. Yeah, if your objective is to get more fragment, if your objective is even to reduce your prediction and all that, within this stage, once you have this rock mass and you have this index in here, it fits directly into this, and you can come up with your drill and blast parameters. So this drill and blast parameters is now developed for each of the domains that you have actually defined. Then you go on to develop your blasting block model. So your blasting block model now has all the blasting drill and blast parameters for each of these domains. Then you implement your model. You measure your key performance indicators, which we'll talk about. But every mine might be unique. Your key KPI might be different from mine to mine. Then what you do is you now calibrate your model with real data. Mind you, all these BI, whether it's LILI, whether it's Ram, all these, whether it's JKR, MSC, whatever you are using, HB, all these, they actually develop their equation based on, if you look at the LILI, it was more based on an iron mine. If you look at HB was based on copper mine. So based on your site, what you seek to achieve is, once you have at least what we call the basic. I don't want to use the word standard. When you go to most mines, you have like the standard drill and blast parameters that is used, for like 3, 4, 5 years. So in this case, what you are developing is your basic, drill and blast parameters. It's basic because it's gonna evolve based on, once you calibrate. So you'll be calibrating your model with real data, and you could use the method of least squares to actually, derive your line of equation, so that your difference and stuff are not so much. Then what you do is you now optimize. Once you calibrate, what is happening is you are now making your data more specific to your site, right? So if you look at this, drill and blast parameters or whatever, objectives that you want to see, you are building, a model for your site, whether it's whichever metal or whichever area. Then so it's more like a cycle. I call it like a cycle. This is more like a model of, you keep on improving it. So, you reach a point whereby, especially if you've not opened another new pushback, you reach a point where you understand your pit very, very well. And again, so once you also have, all these inputs, all these things goes back into inform your new, drill and blast parameters. Now, these are some of the inputs. So if you look at the BI, which I've spoken, you need your rock mass description. So if you're a mine engineer developing such a model, this is something that at the beginning you need your geotech guy to be very, very close and understand, what you are actually doing. Then you need your joint plane. So this is more based on, if you look in here, it's more based on whichever method, whether the LILI, the HB, or the JKRMC by Scott, right? Then your drill and blast parameters, to definitely you need your drilling pattern, your explosive density, your explosive energy BI. So this is where also you work around with various models like the Kuzram, which we'll talk about in the next slide. Then you also definitely you need, what are your bucket capacity. So all these have to feed into getting your right size at the beginning. What shovel cycle time are you looking at? What is your track shovel? So what are your productivity? What do you seek to achieve? When you come to the crash tattoo, definitely what is your open side setting? What is your closer? What is the maximum size rock that should be your largest? After blasting, you have to consider that. You don't want to choke the crusher, right? What is your PAT, FAT? And again, so this approach, as I said, it's not a one-man thing. It's a whole team, a value chain. You have to, have a team of both from mining, processing, engineering to sit down to be able to actually come up with, all these input parameters. So your bond, working index, you have to identify all these things. Your segment, what is the power? All these, input parameters. So these are some of the, I wanted to show, as I said, Kuzram. I wanted to show this fragmentation prediction, model. We have various types, right? It's not just one. So if you look in here, we have the Kuzram, and we have the modified Kuzram, and based on a paper by our very own Dr. Bright Afum and Bruno, and I think Timmins. I think they did a comparison with the various fragmentation prediction model, and I think the Kuzram model state. But other books too says this. you could try both, right? You could try the Kuzram, or you could try the modified one, whichever actually gives you the optimum. That is what you go for. That is, even if you want to go for the crash zone model, CZM, if you want to go for the KCO, which is the Kuznetsov, Cunningham, or Targnoni, model, if you want to go for multiple blasto fragmentation, MBF, or even if you want to go to the SP frag. So it depends on you. But again, based on most papers reading, this is a bit, more, I would say more a bit easier, and also you could see if you look at the, especially normally one thing I like about the Kuzrom is whichever your objective is, you could actually find a subject. So let's say I want a particular, powder factor, and I know my size. So after talking to the processing people, my SM, that is the classification sizes, maybe they want probably 50 mm. So, and I want to know the powder factor, to be able to achieve that. So you can just make this the subject, right? Then you because you know this already. If you want to know this, like you've done with all your, what do you call it? Your rock mass, properties, your fragmentation, the quantity, the charge, weight, strength of explosive relative to the harmful. If you know all these parameters, you can actually define, the characteristic, screen size that you're looking for. So depending on one good thing, depending on whatever you're looking for, you can actually, tweak it to, suit your objective, right? To be able to come up with the right, drill and blast parameters. And one good thing too, the uniformity coefficient too is also very good. So when you talk about the Kuzram, it's actually made of these three. It's made out of the roasting Ramla, and you have the Kuznetsov, equation, which was modified by Cunningham, for amphibase equation, but you can convert it to emulsion to be able to, get it. Then you have what we call the uniformity coefficient, also by Cunningham. Then once you have this, you'll be able to, determine your SC and your SM. That's the sizes that you're looking for, your screen sizes. Then the modified. So the modified, actually the modified Kuzram model, what it did was, to modify the A factor. So if you look in here, you have the A, which is more like the rock mass, properties. Just, modified it, introduce a factor in here, and also replace it by the BI. So there's also something that, if you want to use this, so you could see this now, the new coefficient of, uniformity, right? Then the BI, of course, there's the formula for the BI. Based on LILI. So the BI to based on what you are using. So if you look at this equation, it's LILI, BI formulation. So after, as I say, after developing your model based on these models, Kuzram, you could even look at your prediction. So your prediction you could use the method of least squares to actually determine your right vibration and your right air blast that you're looking for. And these are some of your what we call your key performance indicators that you could any mine would like to actually look into. So if you look at the drill and blast, again, some of your key performance, especially as you're developing this model, this should be your key point. So after every blast, you could do your fragmentation analysis using either split dot stop or rig frag, or whichever tool that is okay for you. And I feel that rig frag is a bit more modern and a bit cheaper, economical. So I normally go for that. Then you could also definitely have, as you blast, measuring your vibration, air blast, especially if you are in a what do you call it, like a community, you have catchment communities around you. Definitely you'll have to be interested in these other impacts of even including fly rocks and stuff based on after every blast, right? Then you have to understand your explosive energy, your density, detonation pressure, and velocity of detonation, VOD. Then when you also so once you have this, so every blast you have to also measure what was my productivity. If you have a what do you call it, a dispatch or module for modeler, you could easily, and get all these things. Then again, you have to involve your maintenance guys to, tell them, okay, I've now had a basic drill and blast parameter. I want us to start measuring, as I tweak, as I change, whether I'm increasing the fragmentation. I want to understand, these costs. I know sometimes there are so many, parameters, especially with this, KPI, but you could still, study it and see the effect on even the bucket change and the teeth changes and all that. Then when it comes to the crashing too, again, you want to understand the energy consumption. You could actually get it from them. As you start, you have your baseline. Then, as you start improving and optimizing your drill and blast parameters, you also be measuring these, KPI from the crashing side. Again, you want to be doing some, working this by using the grindability, test. Then again, the same thing as energy. So when it comes to actually with crashing and grinding, you are more interested in, the energy, and you can even look at your throughput. So again, throughput is very, very key here, especially with the grinding here. And with the crashing too, you could also look at how much, tons that you are, per hour. Productivity of your crashing too is very, very key that you could add to it. And again, so at the end of the day, you look at your cost and savings, right? Again, at the end, I also say money is the, your cash is king. It's king, right? You want to see how much you're saving, because that is why you're actually carrying out this work. So this is also one thing. So as I said, once you blast and you develop your model, you could, based on your KPIs, you could actually start modeling. So you actually model your real data, as against, the model that you develop. Then you could find, your line of equation. And again, if you wanted to make it more, you have to understand these things. You have to actually, develop the mean, the method of least squares. The method of least squares is actually very good. Yep. So crusher and mill availabilities and utilization. That's good point. Thanks, Joseph Jansen. Very, very key too. Yeah. Then so once you have these models in there, then you actually, come up with, because at the end of the day, you want to, improve on your drill and blast parameters, from the whole, value chain, right? So you take each parameter, you model, and now, you feed it into your model. Then again, you simulate to obtain optimized parameter. As I stated earlier, this is the point that you are interested in, right? You don't want it to be, too fine. Again, you don't want boulders, right? So you want a point whereby, you have the minimum cost per ton, right? At the expense of, getting your milling and everything at the minimum, minimum cost, optimum cost, and your crashing and your milling, right? So I always say this is your target. So as you model, you should also take into consideration, these curves to be updating, gradually. So the next is, just to look at how this was applied and some of the case studies that has been done. So this is a typical, case studies, and from these case studies, you realize that you could make it simple and use what do you call it, an SL base, but currently the new graduates, some of them are very, very good. You could tax them, what this is what you want to do, and they could. So this one thing that one of the guys did, he actually programmed, using simple even VBA, to actually do, so that it makes the updating of the data simple, instead of typing. So all the formulas are based, they are calculated, or you can even use a Visual Basic, to develop a simple program to be able to update it. So this a case study that was done. So you have your resource model again. So the geotech, the help of the geotech, they actually classified the pits based on the rock mass classification. We got our plasticity index, blastability index for each domain. So I think we came out with like 4 or 5. Then based on that, we had a blast estimator. So this This actually, has the Kuzram, any model that you want to use. So it has all these built into the program, right? And again, this is the in-house, made program, not, we didn't buy it from anywhere. We just made it in-house. So you have the blast, estimator, and based on these domains, once you enter in there, it gives you, how your basic drill and blast parameters should look like based on, again, all your objectives, right? What you are concerned with. Then you have a data logger that you enter to feed into it. Then it actually also plots to you. The Kuzram model, if you use it very well, you could actually see how your particle size distribution and everything is going to look like after your blasting, right? Then we also had a blast cost. So at the end of the day, how much are you also spending to blast, right? Then we also had this in there. Then this is the blastability blast master block model. So this all these actually feeds into your block model, so that anytime you want to blast, you once you put a polygon in there, you know that, okay, these are the parameters that I have to use. Then definitely we actually designed and implemented it. We did these are so these are your KPIs. So based on what you want to do, you then measure, right? Then it goes back into your system fragmentation analysis, productivity, crusher throughput, and energy mill throughput, utilization, and all that, right? So again, so apart from what you could see, mine-to-mill is something which is proven, right? And again, it should be done integrated. It shouldn't be, be done, in silos. So it's something which has proven to actually, work well for most mines around the world. Would even product increase of, ranging between, as low as 30 to as high as even in the 60%. And you could have, I think, a half for a Diapre mine, gaining so much, from this, process. Again, one other thing I also realized is a team gets together, they actually work it out, they improve of it, and at the end of the day, once the achievement have been done, that integrated team, dies off. So this is something that has to be, encouraged even if it's every, 2 months meeting or anything, just to, align and get ahead of it. Because at the end of the day, especially if you're opening a new pushback, you need to reestablish, all these parameters, based on, the geotech, parameters. If they are similar, you apply it or you change it, right? So it's an ongoing thing. It's a continual, improvement thing. So these are some of the upstream, benefit. Again, you could see these are some of the just a snapshot of what is done. You see this was how it was, and this how we really wanted it to be, right? So you could see now we have a bit of more fine. It's more, distributed, right? The PSD is more, distributed, and we achieve our D50 at 68 as compared to, first, 255. You see from the energy, side of excavator dig rates, actually improved. You see the loading time actually, improved drastically. Yeah, productivity is also, improved. You could see the trend. It's actually, going up. Then you have, again, one other benefit you also have from the upstream. So you could see this is the upstream one. That's from even from the mining side, we kind of have a lot of, benefits by doing that. You have greater variability in track loads, reduces average load factor from 95. So if you compare this to, if you have good fragmentation, you could feel the track. Whilst if you have bad, you don't really feel the track very well, and you get to lose, an amount of track loads that you actually move. And again, these are some of the other benefits to lower maintenance cost, as a bucket, cylinder, ring. I think these are some of the things that, you could also measure to see, some of the benefits, right? Then when it comes to the downstream, so the downstream is looking at the crushing, the milling, I would say the people that we provide services to, right? So if you look at it to the throughput, actually, looking at it, it actually went, very on a very high side, right? We had I think around 4% or 5% increment. Then the power of the crusher, also, you could see it actually went down. which, it's also a lot of savings. No throughput, same, it actually went up, and less worry rate of sag mill and ball, ball mill liners. Yep. So conclusion. Again, as you see, if you look at the process, we had substantial, increases in mill throughput, and reduction in mill power can be achieved by moving some of the breakage back down the production chain to the primary crusher, mine. And integrated mine-to-mill approach, it actually allows a range of, operating strategies to be simulated and evaluated for different ore types in the mine and the plant. So as I said, this you develop it to make it ongoing. It's not a one thing. You don't develop a standard, drill and blast parameters. You actually develop the basic, then you improve on it. And you could, as I said, it has to be applied over the life of mine. The models could be combined with the mine plan to even generate production forecast. So one good thing about this model is once you have it, you could even, you could alter things in it because you have everything built in there. And you could say, okay, what if I want, my fragmentation to increase by this? What if I choose this borehole diameter? It's a very good, tool for you to use. And I could say it's been used very, very well in especially even here in Canada. Most mines have developed a very, almost like 15-year data for these, kind of work. And recommendation, again, to ensure the expected results are achieved and maintained, the recommended changes must be incorporated into managerial decisions. So one other thing that I've realized with the mine-to-mill is it has to be driven, from the top, not from the, it shouldn't be from down, but it should be driven, and it should have the interest, from all levels of, management. And high intensity selectivity blasting based on domain delineation can be developed to improve, blast fragmentation in order to decrease energy consumption and increase throughput in downstream comminution, circuit. Mine operations need to operate more efficiently to meet, environmental, target as well. And again, we have to improve the resource efficiency to be able to increase the economic return of our projects to make, projects more viable. And new haulage systems like AHS, automated drill rigs, electric trucks, and shovel and input crushing and conveying could also be, assessed in combination. So this is one thing, this is more like something that we, as the mine, we could start, looking at once you develop this model and, we understand it. These are some of the other benefits that we can have, if we have these systems, in place. And pre-concentration using screening, gravity, separation of bulk ore sorting could be implemented to discard barren material, consequently, reducing haulage and downstream processing requirement per ton. So these are some of the things that, we could also, do to, increase our reduce our cost and increase our productivity. Yeah. Thanks, and thank you for listening.